Hello and welcome to yet another lecture for General Physics 2. This one deals with the phenomena of wave reflection and interference. What happens when waves bounce off some sort of boundary and then interfere with parts of themselves? So actually in the first part of this lecture, I've included several concept questions about wave behavior. Those multiple choice questions are mainly review, except for the last couple, which will transition us over into talking about standing waves. So if you are in a time crunch or don't care to review the wave ideas, feel free to forward in the lecture until you get to the slides that are talking about standing waves. That's the new pieces of material that are covered in this lecture. But for those of you that want to have some practice with some questions regarding wave phenomena, here we go. If a person creates a single pulse on a string and the pulse is moving to the right, if we were taking a movie of this and we advanced the movie one frame, what would happen to that knot at point A? Would it be in the same place? Would it be vertically higher, vertically lower, to the right of its current position, or to the left of its current position? Well, the correct answer here is that it would be vertically higher. We're told the wave is moving to the right. And what that means in a transverse pulse like this is that all the points on the string are moving up and down. Well, point A is still on the leading edge of this pulse, so a little while later it will yet be higher, and shortly will be at the peak position above equilibrium before moving back down. While the wave moves left to right, the particle in the medium itself only moves vertically and up and down. How about this one? Same scenario. A person generates a new pulse like the first, but moves her hand up and down more quickly. What would that do to the pulse if you move your hand up and down more quickly in generating the pulse? Would it make it the same size, taller, shorter, wider, or narrower? This would actually make the pulse narrower. The speed at which you move your hand up and down actually controls the wavelength, you can think of this, of the pulse, or the width of the pulse. If I go up to the same height and back down, the pulse will have the same amplitude as before, but if I do so quicker, that makes a narrower pulse. If I do so slowly, it widens the pulse out. How about this one? If you generate a new pulse like the first, but you move your hand up further, what's going to happen to the pulse? Will it be the same size, taller, shorter, wider, or narrower? This pulse is going to be taller. The height at which you move your hand above equilibrium establishes the amplitude of the pulse. So if you go up further, you get a taller pulse as a result. Person generates a new pulse like the first, but the string is tightened. What happens in this case? Will the new pulse be the same speed, faster, or slower? The correct answer here is that the new pulse will be faster. You may recall that in a previous lecture, we introduced a relationship for wave speed. It's equal to the square root of the tension on the string divided by the mass density of the string. And so speed and tension are directly related. If you make the tension greater in a spring, medium like this, then you will get a faster moving pulse. And we're going to use that idea to solve one of our problems in the standing wave section. What about this one? If you lower the frequency of a wave on a string, you will lower its speed, increase its wavelength, lower its amplitude, shorten its period, or none of the above. The best answer to this is that you will increase its wavelength. If you have a string that's set, so your medium is set, in other words, it's made of a certain material, you've stretched it to a certain tension, then all of the physical parameters that control wave speed are set. So wave speed is a constant, and then we're looking at the frequency and wavelength. Frequency times wavelength gives you the wave speed. So if you lower the frequency, you increase the wavelength. If you raise the frequency, you decrease the wavelength. And that pattern is seen throughout many kinds of wave phenomena. How about this one? A string and a wire are each 10 meters long, and they're stretched by the same tension of 30 newtons. So you could imagine hanging a 30 newton weight from each of them. The string has a mass of 2.4 times 10 to the minus 3 kilograms, and the wire has a mass of 1.9 times 10 to the minus 3 kilograms. Which one, if either, will the waves travel faster along? The string, the wire? Neither, because there is a tie or we don't have enough information to determine this. We actually have all the information we need to determine this because we need to know the tension and the mass density in order to figure out the speed. Well, the tension on both is 30 newtons. Mass density is a one-dimensional density. It's mass per length. So we would take each of the object's masses and divide it by the length, but the length is the same for both of them, 10 meters. And so the string has the greater mass density here, and the wire has the smaller mass density, given that the wire has less mass. Speed of a wave is inversely related to the mass density. It's equal to the square root of the tension divided by the mass density. So the material that has the smaller mass density, i.e. the wire, is going to have the greater speed in this case. Now we're going to look at a couple of questions that we haven't actually delved in before. So I'm just looking for you to give your best guess at what you think will happen, and then we'll talk about what the answer is. There are also several workbook exercises that practice this same skill in the Chapter 16 workbook questions. So if we have two pulses that are moving towards one another as shown, one is kind of tall and skinny, one is shorter and narrow and wider. What happens when they overlap? Which of those patterns shown do you think you will actually observe here? Well, the best answer, and this is a theoretical model because you can't make exactly square pulses like this, but they're easier to actually think about with adding, is option B here. What's happening when you make a pulse above equilibrium is you moved the spring up and down, and so that energy is pulling the spring up above its equilibrium position, and the wave is traveling along. Similarly, to make a pulse below equilibrium, you pull down for a bit, and that energy is pulling successive parts of the spring down. So when they actually overlap and get in the same location, those two effects are working against each other. So the pulse on top is trying to pull the spring upward. The pulse on the bottom is trying to pull the spring downward. And you can see that the height of the one that's pulling downward is about 1 unit below equilibrium, where the one that's pulling up is about 3 units above equilibrium. So when they get right on top of each other and they're occupying the same real estate on the spring, the one pulling down with 1 unit and the one pulling up with 3 units, the net result of that is an upward pull of 2 units. You use ideas of superposition and opposing effects here. So if you see B here, this is 2 units tall in the middle, the places where those two pulses overlap. And then off to the side, there's only the shorter, wider pulse, so we see the remnants of that shape right here. Wouldn't be C, because C maintains the overall height of the original pulse on top. And A is even taller, so B is the best answer in this particular case. Though realistically, again, you can't make really square pulses, so E is probably the most realistic looking pulse you could generate on a spring. All right, one more of this same thing. If the two waves shown below were moving through the water at the same time, what would the surface of the wave look like? So pay close attention to the shapes of those and see whether you think it would produce A, B, C, or D. Well, the best answer here, I believe, is option D, because if you look at the left-hand parts of both of these, when wave 1 is above equilibrium, wave 2 is below equilibrium by an equal amount, and being above and below by an equal amount produces cancellation. Then we have a part that's above equilibrium, but that cancels the part that's below equilibrium. So these pulses on the left cancel out and show no pulse, which is a feature of A, B, and D on my choices here. On the right-hand side, though, they're both below equilibrium at the same position, so that's going to pull the spring even further below equilibrium. And then, likewise, they're above equilibrium at the same position, so that's going to pull the spring further above equilibrium, which produces a taller spike both above and below equilibrium, which is what we see here in option D. So that idea of pulses running into each other and interfering with each other is at the heart of what we're talking about when we talk about standing wave patterns. And we talk about standing wave patterns in this class primarily in the context of waves moving on a string, but this is actually a model of what's happening when you are playing a stringed musical instrument, piano, guitar, violin, any of that kind of stuff. And the physics involved is the same idea that you actually use to think about standing wave patterns produced in other musical instruments, like ones that are, elaborate tubes of air or your brass instruments and such. So while I'm not going to get into it here, there's more detail in the textbook about those standing wave patterns for tubes of air. So in this little simulation on the screen, we see what would be considered a standing wave pattern on a string. And there are parts of the string that we can see that are moving a lot up and down. And there are other parts of the string which are symbolized with the red dots here, where the string is not moving at all. How do we produce a pattern like that? Well, if you explored the lab, you may have gotten an inkling of this. This is this same animation, or at least the same idea of the animation, though it looks like they have different frequencies. The one on the bottom is intending to show you where the overall pattern comes from. So the two lighter waves are two waveforms that are moving in opposite directions on the string, passing by each other. And places where you see a peak of one of those pulses overlap a peak of the other pulse, the overall pattern gets taller. Where you see what might be considered a trough, a dip under equilibrium, overlap another trough, you get even further below equilibrium. And then when you see a crest passing a trough, they completely cancel out. And so if you watch carefully along these points, which are considered nodes, the two pulses are always opposite height of each other on either side of equilibrium. So fundamentally, we produce a standing wave pattern when we send wave pulses at each other in opposite directions here along a string, and those waves either add together constructively, making a larger overall motion of the medium, or destructively, where they are partially or completely canceling each other out. So these standing wave patterns get characterized with a vocabulary that is used to talk about the patterns and their relationships to one another. So generally, if you did the lab, you saw that as you increase the frequency, you increase the number of these antinodes and nodes that are within the patterns. Antinodes are the names given to places where there's lots of movement. Nodes are the names given to places where there is no movement in the center of those antinodes. So the lowest standing wave pattern you can generate at a given frequency is called the first harmonic, or sometimes it's called the fundamental mode of oscillation here. And it's where you have one antinode in the middle of the pattern. The string is moving up and down a lot in there, and it's fixed on the two ends of that pattern. If you increase the frequency, in fact, if you double the frequency, which is another thing you should have found in the lab, you will produce the second standing wave pattern with, this one has two antinodes in here. And it's also counted as having two nodes. We count the middle node as one, and then we count the ends each as half a node, just so we keep the counting index the same, whether we're counting antinodes or nodes. The third pattern, 3 times the fundamental frequency, produces the third harmonic, or the second overtone. This one has 3 antinodes, and then 2 whole nodes here in the center, the 2 half nodes at the end, 3 nodes as well. Recall that wave speed is the product of frequency times wavelength, and we can write it shorthand, v equals f times lambda. What are the wavelengths that go along with these standing wave patterns? Well, if you look at this first fundamental one, right, if you follow the string up to a maximum position and then back down to the node, you might recognize that you've only completed 1/2 of a complete wave cycle. And so if I was to figure out what the wavelength of this pattern is, I would need to continue following it until I got to the end of one complete, go up, back to equilibrium, down, and back to equilibrium. So the wavelength of this fundamental mode is 2 times the length of the string. Well, what about the second one? Well, this one, you can go up here, go down here. Hey, that's 1 wavelength right there. So in the second mode, the wavelength of this pattern is just whatever the length of the string is that you are producing this pattern on. The third one, let's see, we go up here, down here, and so when we've reached this node right here, we've completed a 1 wavelength here, making the wavelength 2/3 of the length that is in the space there. It's not drawn here in the diagram, but you can imagine the n equals 4 mode, which has 4 of those little humps. In that case, the wavelength is 1/2 of the length, and a pattern like this continues. Well, we can write this a little bit differently, right? You can write the wavelength as 2/1 times L, 2/2 times L, 2/3 times L, 2/4 times L, and you can see a pattern emerging here. You can write it in general as being 2/n times L, where n is an integer value, 1, 2, 3, 4, etc. Frequency is speed divided by wavelength, right? If we rearrange our speed relationship up here. So the frequency is the wave speed on that string divided by whatever the wavelength is. Well, the wavelength is 2/n times L. And if you don't like fractions of fractions, you can move the n up to the top. It's n, an integer n, times the speed of the wave divided by 2 times the length. Well, the speed of a wave is the square root of the tension in the string divided by the mass density of the string. So you can put these all together in a relationship that predicts the frequency of a standing wave pattern for a given node, given the length of the string, given how much tension is in the string, and given what the mass density of the string is. If you did the in-person lab, you actually derived this whole relationship from what is done in the in-person lab. If you do the online version of the lab, the only thing the simulation doesn't let you vary is the length of the string. So we're missing this 1/2L piece of this, but we saw in either version of the lab that the frequency was directly proportional to the number of nodes. It was proportional to the square root of the tension in the string, and it was inversely proportional to the square root of the mass density of the string. So let's solve a sample problem with this idea. Here's a standing wave on a string. You have a string that has a mass of 13.5 grams. If you stretch the string with a force of 9.33 newtons, giving it a length of 1.87 meters, and then you vibrate the string transversely at precisely the frequency that corresponds to its fourth normal mode. So you're producing that fourth normal mode where you have 4 humps in the string. That is at its fourth harmonic. What is the wavelength of the standing wave that you create in this string, and what's the frequency? Well, you don't have to, but I find it helpful to sketch my pattern when I'm thinking about this. So if we assume both ends of this string are fixed, the fourth normal mode would look something like this. And if you trace this pattern, you can see that, hey, the wavelength is 1/2 of that full length of the string. So the length of the string is 1.87 meters. That must mean the wavelength is 0.935 meters. Figuring out the frequency, a little bit more work, but not too bad. Wave speed on a string, again, is the square root of the tension force divided by the mass density. And for any wave, we know that speed equals frequency times wavelength. So if we solve that for frequency, frequency is speed divided by wavelength, and speed is the square root of the tension divided by the mass density. So we get the frequency being the square root of the tension force divided by the mass density, divided by the wavelength of the wave here. And now we know all these pieces because the problem statement gives us the tension. It gives us the mass of the string and the length of the string. So the mass per length is that mass density. And we know the wavelength from what we calculated in part A. So if you plug in those values, 9.33 newtons and 0.0135 kilograms, you need it to be in kilograms per meter if the units are going to work out appropriately here. Divided by the 1.87 meters, put that all in a square root, divide it by the wavelength of this mode, which is 0.935 meters, you would find that the frequency that is required to produce this standing wave pattern is about 38.4 hertz. I just want to end this lecture by putting some questions out there that will have us thinking forward to some phenomena we're going to observe shortly in the domain of optics. So we want to think about what happens in the boundary between media. So we've talked about what happens when two waves meet, right? They interfere with each other. They might add to make a bigger wave temporarily, or they might cancel out either completely or partially to make a smaller wave or no wave, at least momentarily. And we've also talked about in a previous lecture what happens when a pulse encounters a fixed end of something or a free end. So those pictures on the left remind us of this. If a single pulse comes in and hits a fixed end where the string is tied to the wall, it's reflected back on the other side in the opposite direction. When it hits a free end, quote unquote free end, and this ring allows the string to slide freely, the reflected pulse comes back on the same side of the boundary. But what happens when a wave encounters the boundary between two media? Well, first of all, what do we mean by boundary between media? Well, it could be any place where two different kinds of materials meet. So, for example, you can do this with a spring or string. You can tie one spring to a slinky, for example, and you have two springs with different spring constants that are interacting. Or you can tie a spring to a string, or a string to a rope. Any kind of thing like this would demonstrate this phenomena. But sound is another place where we worry about boundaries. So sound changes its properties when it goes from, for example, air into water, or ground into air, or actually air into a body of different temperature air, because the speed of sound is dependent on the temperature of the air that it's traveling through. Geologists worry about this too when they study seismic waves. So, you have an earthquake and you produce waves, and these waves race off through the earth. But along the way, they transition into different layers of the earth, or from ground into water, water into ground, etc. Light waves, which we will look at shortly in this class, are another classic example, right? What happens when light goes from air into, say, water, or into glass, or glass into air? Any combination where light is traveling at a different speed in the different media. Radio waves too, right? A charge moves a certain speed in an antenna, gets out into the air, it travels a different speed in the air then goes back into, the wave through the air goes back into the antenna. So there are boundaries between materials there as well. And broadly, all of these contingencies can be covered by the same rule. When a wave encounters a boundary, it is, in general, both transmitted and reflected, which means a portion of the energy continues on as a wave in the new medium, but a portion of the energy reflects and returns back in the opposite direction in the original medium that this was traveling in. Now, you might get situations where, 99.99% is transmitted and we just ignore the reflected piece. Or 99.99% is reflected and we ignore the transmitted piece. But in general, both of these things happen anytime a wave hits a boundary between medium. So the transmitted wave in the new material maintains its general shape when it moves into this new material. But it might change wavelength as a result of the speed in the new material. If the new material is one in which the wave can travel faster, its wavelength will also increase. If the new material is one in which the wave travels more slowly, its wavelength will actually decrease. And if a wave moves from a region that is more dense material to less dense material, it turns out that the reflected wave mimics what we see with free end reflection. So recall again, free end reflection, when you have a pulse on a string, that pulse is transmitted back on the same side of equilibrium. It does not change its orientation. However, if a wave moves from a region that is less dense to a region that is more dense, the portion of the wave that's reflected is actually mimicked by fixed end reflection, where the pulse switches its orientation relative to equilibrium. Where we're going to see this moving forward is when we look at what happens when light as a wave encounters boundaries between layers of materials. And so these fixed end and free end models help us understand what we see in the behavior of light that is both transmitted into the new material and reflected back through the old material.